Today, we're going to introduce material on the last chapter for the semester, chapter 9. And it's an extension of what we've covered in chapter 8, concerning orbitals. We're going to focus on covalent orbitals and try to solve some problems that we had, well, that everybody had, scientists had, with the valence bond theory, with a tweak. You remember in the beginning of the semester, I said, what do you do when your theory fails? You have three options. You can either ditch it, start over. You can restrict its application to areas where it does work, or you can modify it. And what we're going to look at first is I think just one modification, well, maybe two modifications of valence bond theory and the models that accompany it to extend its usefulness. And then as soon as we get through doing that, we're going to ditch it and go to something else. Actually, it's still useful under certain circumstances. We're really not going to ditch it. We're going to restrict its application. All right. So, y'all want me to turn that off? Is that bothering anybody? Okay. So let's see. All right. So one of the problems we have with the VSEPR model in predicting structures is that it does predict a structure for, and we're going to use methane as our example. We know that it's going to predict a structure for this one because if we draw the Lewis structure, right, and there are no lone pairs, we draw the Lewis structure, this predicts a tetrahedral structure. Okay, and that's true. Experimental evidence does say that this is a tetrahedron, right? And what are the bond angles? You remember that? Those are the only ones that you really had to memorize. 109.5, right? And that's true for this one, because we had no lone pairs, so there's nothing pressing on those bonds to make them shrink. So this is the actually, let's round it off. It's like 4817 or something like that. That is the actual bond angle for this molecule, and for any molecule that is symmetrical like that. Carbon tetrachloride would do the same thing. All right. So the problem arises, but remember the valence bond theory says that each atom that's bound to another atom shares its electrons. Those electrons still belong, and the orbitals they occupy still belong to each individual atom. And the valence bond theory says that the ones that are responsible for the bonding are the valence electrons. So the core electrons don't enter into bonding, and that's still true for any of the tweaks that we're going to do. But when you do that, that means that what bonds does what orbitals does hydrogen have available to it? Remember our electronic structure, it just has one s with that one electron. That's all. That's a spherical shape. Oops, can't spell. That's a spherical shape orbital. Okay. What does carbon have available to it? Now, if we draw the carbon structure, let's see, it's 6 electrons. So we have 1s2, 2s2, 2p2. Okay. Well, with the valence bond theory, if these electrons belong to it, these are the valence electrons. We've got 2 in spherical orbitals and 2 in those dumbbell-shaped orbitals. Okay. You can't attach these 4 of these two over here and two over here and get a tetrahedron. Right? Because the spherical overlap of these two could put them anywhere. And the overlap of the two P's, of course, would fix them in a reasonably local shape. So there's the problem with the valence bond theory. These valence electrons and their orbitals don't allow us a tetrahedral shape. Okay, that's the problem. Let's see, S2, P2, and then I just said there. Okay, so what are we going to do about it? Well, like I said before, the first thing we're going to do is try to tweak the theory, make it work, right? And this proposal that I'm going to show you was given by Linus Pauling in 1931. And you know, I think I said this. He got a Nobel Prize for his explanation for the nature of the chemical bond. Right? So he should know what he's talking about. But he proposed, let's see, it's not on that slide. Oh, I'm going to talk, am I explaining some more of the stuff? 4 equivalent orbitals, okay. All right, so that just says what I've already told you. We know that the shape is tetrahedral, but we can't explain it with the valence bond theory presently. We have to modify it. It's called hybridization. So what we're going to do is take those orbitals for carbon and just the bonding orbitals, right? The 2s and the 2p's, and we're going to create a hybrid orbital called sp3. And there are going to be 4 of them, right? This hybrid orbital, you have the same number of hybrid orbitals as you do of the atomic orbitals from which they're derived. It's a process called, I guess you call it mixing. You're mixing the orbitals to come up with something that will behave. Okay. All right, that just further explains the problem. Right. So we don't need to dwell on that. This was Linus Pauling's tweak, and he developed the terminology for hybridization of atomic orbitals, and they're still atomic orbitals. They still belong to carbon, right? And they don't exist until the bond forms, right? You can't get these in a free carbon atom. You only get it when it's needed. Okay. And the equations, remember the when we sort of alluded to the quantum mechanical theories and the equations that were developed by Schrodinger. When we were talking about individual atoms and the electronic structure, well, those can be extended to atoms that are behaving in bonding situations. Right? So they had to be modified. Those equations had to be modified, and that's beyond me. So that's as far as you need to go with that. Let's see. Here we go. Let's see. Combination of 1s and 3p orbitals. So here's what we're doing. There's only one s orbital here, right? It has 2 electrons in it, but there's not just one s. But there are 3 p's here. And under the atomic situation, you've only got 2 electrons in those orbitals. But we need a place for 4 electrons. So we're going to take all 3 of these and combine them with this 1s, and that's where we derive the sp3. In this case, the sp3, I guess this could refer to three electrons. No, it's 3 P's. So just have to get used to the way it's written. Rather than writing SP and 3 down here, we write 3 up there, which can be confusing because now we're not talking about an element where you have 3 up here as a charge, or 3 up here is the number of electrons. It means there are 3 P's that go together with 1 S to make that hybrid orbital. Okay. So superscripts depends on your what you're talking about as to what the superscripts mean. All right. And when we do this, we get the tetrahedral arrangement. You have 4 hybrid orbitals, and you're still valence shell electron pair repulsion. You're still spreading them out as far as possible from each other, and that gives you the tetrahedron with these hybridized orbitals. All right. So one of the things that the valence bond theory never has been able to do is to predict actual calculatable energies for the bonding electrons. We can only speculate that when we're talking about these, well, the quantum mechanics does predict energies. It does do that. But once you start bonding, you can't predict the energies anymore. Not reliably. What you're going to get is there it is. Okay, I can see it better over here. It's not making a big arrow here like it does on my screen over here. What we can say, though, is that the p orbitals are higher energy than the s orbitals for the second period. And then the hybridized orbital is somewhere in between. And we assume that since the p orbitals start off higher than the s, and there's 3 of them, that the hybridized orbital is going to be closer to the p energy than it is to the s. That's about all we can say about it with any degree of accuracy. All right, so we get these, the 1s and the 3 p's on your left, and then they hybridize into these 4 equivalent hybridized orbitals that are pointing to the apexes of a tetrahedron. Okay, and they've got the calculations. This is what the quantum mechanical calculations show you is the most probable shape. You have a big blob on one side and a little blob on the other side. Okay, and that now the hydrogens, they don't have to hybridize. Right? They just got the 1s orbital with their 1 electron, and they share it with one of these and its electron, because this has 4 electrons in it, right? 2 from here and 2 from here. So the hydrogen doesn't have to hybridize, just the carbon. All right, how would this look with a different molecule like ammonia? Well, we know that ammonia's electronic configuration, electronic structure is tetrahedral, right? And we've drawn it, represented it like this. Right? You've got this hydrogen in the back, you got a hydrogen out here, hydrogen out here, and they form that triangular base for the tetrahedron. And then up here, you got a lone pair to form the apex of the tetrahedron. What does that do to our tweak? Okay, that didn't show up over here. All right, so we're gonna hammer this idea a little more. First, you draw the Lewis dot structure. We're still in the valence bond theory. Draw the Lewis dot structure. Determine the arrangement using the VSEPR rules. Right. Then determine how many hybrid atomic orbitals you need around the central atom to accomplish the bonding in that configuration. Okay, so for ammonia, we would get this Lewis dot structure. This is more trying three-dimensional here, but that's a valid structure. And you have the need for 4 hybrid orbitals around nitrogen, because you've got 3 bonding and 1 lone pair, and you've got to have a place to put them. So we hybridize nitrogen the same way we did carbon. We have an sp3, and this hybridization is based upon the electronic structure. All right. All right. 3 of those sp3 hybridized orbitals. This is an sp3 here, and this sp3 here, and an sp3 here, and an sp3 here. That sp3 that I've positioned up here is filled by a lone pair bonding orbital. Dropped out, came back. So that's what it would look like. Now, its bond angle would start off at 109.5. But because, and it still holds, that these lone pairs, they tend to balloon out because there's no bond that's confining them to between atoms. So what they would do is add pressure to these bonds and squeeze them down. I think we saw somewhere it was like 107 degrees. It shrunk a little bit. Okay, how about this one? Ethylene or ethene is another way of saying it. This is an organic compound. And it's just 2 carbons hooked together and 4 hydrogens on the outside. So what's the shape of the ethylene molecule? Well, it's going to look like, let's do it like this. Let's follow the rules. Okay. So we've got carbon has 8. We got 8 electrons here and 4 there, so we have 12 electrons. So we have a carbon hooked to a carbon, and then we have the hydrogens here like that, right? 2, 4, 6, 8, 10. Okay. So we have 2 electrons. Can't put any more on the hydrogens, so we'll have to put them here. But we've got to make an octet now. We have an octet here, but not here. So we'll put that one there, and that gives us this structure. This is our Lewis structure. And what you may notice is that how many groups are around each carbon? There are 3. So each carbon is going to behave exactly the same. We describe one, we've described the other. So with 3 groups around here, what does that mean? Trigonal planar, electronic, and molecular, because we have no lone pairs. So how do you get a trigonal planar there? Well, you don't need 4 hybrid orbitals anymore. Right? You only need 3. So how do you get 3 hybrid orbitals? Well, you use the S from the carbon. We start from the lowest energy and work our way up. But we only need 2 to make equivalent 3. 3 hybrid orbitals. So you would have an sp3, sp2 here, sp2 here, and an sp2 there for one of those bonds. But we've got a double bond. So where did that double bond come from? Well, if you've got the same hybrid orbitals over here, then you've got an extra p orbital that was not used for each of these atoms. Then we could draw it like this. So it's got 3 hybrid orbitals and then an unused p orbital for each one. So what you do is you get an overlap of those 2 p orbitals, and that's where your double bond comes from. And the subsequent slide should show us bond angles are 120 degrees, right? It's a isosceles triangle with an atom in the middle. And if you're going all the way around at 360 degrees, divide it in thirds, that's 120 degrees. Okay. So sp3 won't work in this case if you give you too many. You don't need sp3s. sp2 will do the job and just leave one of those p orbitals hanging out there until you use it to make the double bond. And the one that's the single bond that's on axis between the carbons is called a sigma bond. And then the one that's off axis between these two right here, that's called a pi bond. Okay. Sigma is always on axis and you can only have one. But there's only room for one sigma bond. But there's room for a couple of pi bonds. You can either have it in this plane or that plane. So that's how you get a triple bond. You just have 2 pi's and a sigma. Okay. All right, so that's a description that I just gave you there. And this is in black and white. Flashing black and white. All right. So when we look at the energy profile for these hybrid orbitals, since there are only 2 p's involved now, the energy level for the sp2 is a little bit lower. And the 2p that's left out is at the same level it was. All right, so there's the unused p orbital, shows you there. And let's see. And it's going to be perpendicular because the trigonal planar is what it says. It's in the same plane. So at right angles to that plane is where the p orbital lives until you bond it. So there's your sp2 calculated profile for the orbitals. Let's see. All right, and this is sort of a artist rendition of what the overlap would be. These guys are perpendicular, so they overlap, and the overlap is not as complete as a sigma bond. A sigma bond has more overlap. It's more stable than a pi bond. A pi bond does increase the stability or decrease the energy overall, but it doesn't go as far as a sigma. So for that's why in the past I said that a double bond is stronger than a single bond, and a triple bond is stronger than a double. But usually the double bond is not twice as strong as the single bond because there's not that complete overlap that you get that would stabilize it more. All right. So how about carbon dioxide? What would it look like? Well, we've drawn the Lewis dot structure of carbon dioxide so many times, we shouldn't have to go through that procedure. It's going to be like that and dioxide. Carbon dioxide. Here. Here. Yeah, like that. 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. Okay. We've got all octets there. So that's what the Lewis dot structure should tell us, that it's linear. Linear with respect to this carbon and linear with respect to that carbon. So it's like if A equals B and B equals C. So if this is linear and if this is linear with that one, then that one's linear. That one, whole thing is linear. Okay. So the bond angle will be 180 degrees for either carbon. All right, so how do you get the right hybridization for this carbon? Well, you only need two, right? So this is going to be, since it is linear, you only need two hybrid orbitals in order to make that a linear bond, a linear profile. So that would be just one S and one P. That's all you need. You got one SP going this way, one SP going that way, because you formed it from one of these, one of those. That means there are two of them. You have two SP orbitals. One of them is bonding that side, one of them is bonding this side, and that leaves how many unused P's? Two. So you got one that's right angles this way, and another one that's right angles that way. And the same thing for the other carbon. Right? So one of those p orbitals, and actually, if we look at this oxygen, what would be the hybridization for the oxygen while we're at it? Right? 1, 2, 3. This would be trigonal planar. So oxygen needs sp2. And it uses one of those sp2s to be a sigma bond with carbon. It uses two of them for these lone pairs. And then it still has an unused P that overlaps with one of these. Okay. And then on this side, you get the same thing. And this one overlaps with, let's see. Yeah, this one's got that. So these overlap here to make another pi bond here, and these overlap. All right, thank you. So you got your sigma bonds and your pi bonds accounted for with these hybrid orbitals or unused P's. I think they're okay. Well, the energy profile means since two of the p orbitals are unused, they're going to be at the same energy level as they were before. And the sp orbitals are going to be even lower than the sp2s because you don't have the higher energy p hybridized with it. And they're on axis. So there you go. You get your overlaps. So there's a pi bond in the making right there, and there's another pi bond in the making right there between the oxygen and the carbon. Oh, nobody said anything.
Extra carbon.
Yeah, I got an extra carbon.
I thought you messed up with the clause.
No, no. The reason I have the slides is to keep you from messing up. Right. Carbon dioxide. I wonder if that's a real compound. Okay. The logic is the same, but it's based on a different diagram. Let's see. What would that be? Could you have a C2O2? I just drew it. It looked like it was right.
It looked legit.
Yeah. Okay. Did I leave that in the recording? To show everybody I'm human. Okay. So it's just another way of looking at it. Got that arrow sticking around. Okay, the last one before we move on to something else. How about dinitrogen? We've drawn it before, and it has a triple bond, right? One sigma, two pi's, and lone pair on the ends. And so how would we hybridize this nitrogen? It would have to be sp because it's linear. This one would be sp. And one of the SPs would go to this sigma bond between the two. And then the other, since we have two of them each, and the other would accommodate those lone pairs. Then the unused p orbitals would overlap to form the two pi bonds. Let's see. There we go. There we go. SP hybridization. Okay, I think I've got a chart coming up after this that puts everything all in a nice, neat little package. Okay. Oh no, we're going further. Yeah, we do need to go a little bit further before we put it in a table. All right, PCl5 is an example of what kind of molecule. Well, if we draw this one out, what we get is no lone pairs, just 5 chlorines. Right, so we get this 1, 2, 3, 4, 5, like that. And all these chlorines have their octets. But how do we hybridize orbitals to give you 5 equivalent or that will fit the VSEPR model? This would be what? It's a trigonal bipyramid. Remember that? So you got this, and then you got the phosphorus in the middle, and you got a chlorine up here, you got a chlorine down here, you got a chlorine there, chlorine there, chlorine there. So how do you? SP3 has used up all our S's and P's, right? So where do we go from here? Well, look where phosphorus is located. Right? Phosphorus is in the 3rd period, right? It has access to d orbitals. So we need to add a d orbital. So a d sp3 will give us 5 equivalent hybridized orbitals. Okay, you can't do that with the second one, right? It doesn't have access to d orbitals, so they're stuck. And that's okay because we don't see any of this type of structure with these molecules, or these atoms, excuse me, as central atoms. So DSP3 gives you 5 hybridized orbitals and accounts for a trigonal bipyramid with bond angles of what? Well, let's see, bond angle here would be 120, right? Bond angle here would be 180. And a bond angle, let's see, how do I draw this? A bond angle between, say, this one and that one would be a right angle. So that's 90 degrees. So you got 90, 120, 180.
How would they get confused the D orbitals when they don't start until the next period?
Well, what do you have if n equals 1, 2, 3, 4, say? How many L's do you have here? Well, you can only have a 0, right? That's S. 2s, you can have a 0 and a 1, or an SP. But the 3rd period, you start having access to SPs and Ds, 0, 1, and 2. So even though it's not used, phosphorus doesn't use it as an atom, as an electronic structure for the atom. They're still there. Yeah. And we don't have any other choice. Okay, trigonal bipyramid, and there it is, 91, 20, and 180. Okay, DSP3, so it produces 1, 2 plus 3 is 5. So you need 5 equivalent orbitals, hybrid orbitals, to give you that structure. And that's what an artist would think of it. And of course, the chlorine doesn't have to hybridize. Right? It just uses one of its p orbitals. Right? Remember, chlorine's got 7 electrons, right? And two of them are in s orbitals, and the other 3, no, that can't be right. Let's see. Chlorine has 3s. I'm thinking of valence only. It has 3s2, 3p5. Yeah, 3p5. That's right. So it has these orbitals here. Right? It has this one that's incomplete. So it overlaps this one with one of the hybrid orbitals. And that's how they share electron and form the bond. All right. We go from sublime to ridiculous now. Xenon tetrafluoride. Right. When we drew this one last, we had maybe I better do that. And have this, fluorine. Let's see, we had 8 plus 14 is 22, right? 22 electrons. I calculate that right. 8. Yeah, 22. So we got 2, 4, 6, 8, which would be 14. So 2, 4, 6 times 4 is 24. Well, that's not right. That can't be right. I miscalculated somehow. That's 8. This is 7 times 2. It's 14. Yeah, it's 22. Right? 2, 4, 6, 8. That's 8. 14, right?
It has XEF4,
5 and then 4.
7 times 4, right?
Oh, yeah. I can't multiply. 28. 28 plus 8 is 36. That makes a whole lot more sense. So if we subtract 2, 4, 6, 8 from that, we're back down to 28. And now we have 6 for each fluorine that we need to count for. 4 times 6 is 24. We have 4 electrons left over. They have to go on the central. So now we have 6 groups that go in, and we know that VSEPR says that's octahedral. So we have that square. We have xenon in the middle, something here and something here, and we put the fluorines on the square, and the lone pairs go up here. So the electronic structure is octahedral, which means we need 6 hybrid orbitals. So we're going to use 2 Ds this time. So that's 3, 4, 5, 6. That would be the hybridization for octahedral electronic structure. And the bond angles would be, they're all 90 degrees, right? 90 degrees here, and 180. Got one there, and then we've got these with each other, and this one with the bond. Actually, the bond angle, that wouldn't be a bond angle because there's nothing up there. So the bond angles are only 90 degrees, right? Just on that square. I had to convince myself. No, that's not right. That needs correction. You can't have a bond angle with a lone pair of electrons. Oh, I don't know where I come up with that one. All right. So it's not always the pressure of the moment that I make mistakes. I can do it in the privacy of my office. Okay. So that's D2sp3 hybridization. Uses 6 equivalent orbitals. And the shape experimentally is determined as square planar. And our theory then has to adapt to that. So that's why we put all the fluorines around the square, because that's what the experiments show. And the lone pairs have to be included in the hybridization because of the VSEPR model says they do. The electronic structure says that they have to be in there. Okay, there's my table. So this is an extension of our VSEPR discussion. When you have 2 effective pairs, you got linear, 3 is trigonal, planar, tetrahedral, trigonal bipyramid, and octahedral. And then you can just go over here and say, all right, you only need 2, so I got 1 S and I only need 1 P. Here I need 1 S and 2 Ps. Here I need 1 S and 3 Ps, depending on how many effective pairs you have, or groups, I call them groups. And then if you need 5, you just add in a D, or if you need 6, you add in 2 Ds. Okay. There we go. Okay, let's see. Is this one going to throw us a curve? Hydrocyanide. This is hydrogen cyanide. Because it's not in aqueous solution, so can't call it. Can't use the acid naming convention. All right, so if we draw this one, we've drawn this one before. Like that, like that, like that, and there. So that gives us a duet here, octet there, octet there. Okay, what's the question? Let's just draw all of them. C and N both hybridized. Right, so this is linear here. This is linear here with that lone pair. So this is going to be sp hybridized. This will be sp hybridized. And this one has 2 unused p orbitals. This one has 2 unused p orbitals. And they overlap to give us the 2 pi bonds here with the sigma bond in the middle. So they're both sp hybridized. There's your sigma. There's another sigma. There's a pi. And there's a pi. Okay. Okay, I guess they're going to try to stump the band. Determine the bond angle and expected hybridization of the central atom for each of the following. We've already done ammonia. Okay. We know ammonia needs sp3, and its bond angles are going to be nominally 109.5. So we can set that one aside. Let's see. There we go. Which one's next? Do SO2. Okay, SO2. All right, so SO2 has sulfur 6 valence electrons. 3 times 6 is 18. We have 18 electrons. We need a sulfur, an oxygen, so that's -4. And that's 14. So we have 2, 4, 6, 8, 10, 12, 14. Okay. Okay. That's the Lewis dot structure. Now, if we got 3 groups, that means sp2. It's trigonal planar electronic structure. Of course, molecular structure is going to be bent. So what would be the angles? 120 degrees, right? There we go. All right, I guess we're going to krypton difluoride next. Okay, so we got 8 here. Now we got two fluorines.
That was
22 electrons. There we go. Okay, so we got krypton and fluorine and fluorine. So that's -4. Right? Yeah, 18. Okay, so 2, 4, 6. That's 12 more electrons used for the fluorines. Means 6 here, so we have 2 there. So around the krypton, we have 1, 2, 3, 4, 5. We need 5 hybridized orbitals. So that's D, S, D, 3. All right, now where do these lone pairs go? Logic would put them on the triangle, and that would make this linear. Is that what we get? Yeah. So this would look like this, and we would have krypton in the middle, and then fluorine up here and fluorine down there. That would be the most efficient arrangement. So we need 5. D, 1, 2, 3, 4, 5. Same, GSP3. But the bond angle will be 180 degrees because these are the only atoms in that molecule. Do that. Make room for the next one. I guess we're going to carbon dioxide. We did that one already. Sort of. Yeah. So this is going to be linear. That means we need SP. And the bond angle is going to be 180 degrees. This one. Yeah. And the last one, ICL5. Okay. I could take a wild guess, but we better do it right. 6 times 7 is 42, right? 42 electrons. So we have iodine in the middle. 1, 2, 3, 4, 5 fluorines. Yeah. 2, 4, 6, 2, 4, 6, 8, 10. 32. So if we have 6 around each of these left over, 6 times 5 is 30. So we do have 2 electrons left over that have to go on that iodine. So this is electronic octahedral, which means D2sp3. But where did that lone pair go? That's the question. I think for octahedral with a lone pair, the lone pair goes on the square. We got iodine in the middle. We got a lone pair out here. And the rest of them are filled by fluorines. 1, 2, 3, 4, 5. That means that the bond angles will be 180. It'll be 90 at 90 degrees. And that's it. 90 and 180. Yeah. Let's say one. Oh, it left off. It left off this one. Unless it's putting the lone pair up here. Then why would it do that? I don't think I have a ready reference to tell me whether or not that's right. If it's leaving out the 180, then it's saying the lone pair is up here. I think the lone pair is supposed to go on the square. Hybridization is correct. bond angle might be questionable, depending on where that bone pair goes. All right. What do we got? 20 more minutes.
We might be able to make it. I'm not gonna make it through the whole chapter today. Yeah, okay, that's good.
We'll finish up on Thursday. All right. All right, you've seen this one before. We don't need to hammer that one anymore. So what are the limitations of a localized electron model? Well, let's see. We've learned since that it incorrectly assumes that all the electrons belong to individual atoms. And they only bond by sharing temporarily in the bond. They don't actually do that. And one of the clues is that we have to invoke resonance for some Lewis dot structures. Right? Nitrate ion is one that we talked about. So that's one of the places that it stumbles. It doesn't deal with molecules that have free radicals. In other words, unpaired electrons. What do you do with them? And I mentioned this one earlier. It does not effectively predict the bond energies. We just sort of ballpark it. Okay. So that's where that's a good breaking point, because the next slides go into molecular orbital theory. And this is probably enough for your brain today. I know it's enough for mine. Any questions? Okay.